Swayam Prabha. Digital India. Educated India.
And point hyperplane duality. So, Arijit Vishnu already introduced some of these things. I will just do it again in general dimension, like for general D, not in dimension 3. Okay, thank you. Okay, so we have already, so what are the definitions we have already seen? So let's recollect that. So one is, so recollect, first is affine independence. So remember, I will be working in all of the things will be in RD. Okay, so affine independence. Okay, the second thing I will need is convex hull. Okay, so these definitions I will not repeat. Okay, good. So let's say, let's define a simplicial simplices or simplex. So definition 1. So let's say you have a set of points P1 to Pk in Rd such that k is less than equal to d plus 1 and they are affinely independent. So we can define what is called a simplex sigma, so which will denote like this: sigma of P1 comma square bracket Pk. Does not matter what order you put it. Okay, so it's okay. Simplex sigma will be a convex hull of the points Pi's. Okay, so what are we talking about? So just let me put it down. So let's say if it is only one point P1, then it's just a point. If it is, there are 2 points, then it will be the line segment connecting the points. If there are 3 points P1, P2, P3, then it will have been the triangle. If you have 4, so let's say these 4 points are in R2. Okay, can it define a simplex in R2? No, up till 3. Okay, has to be less than equal to d plus 1. Okay, but this does define a simplex in, these are called tetrahedron, right? Tetrahedron. Okay, so this will define a simplex in R3 if the points are in R3 and they are affinely independent. Okay, so we can also define dimension of a simplex. So dimension of a simplex, so like if the point set is, let's say if the simplex is like this, P1 to Pk, then the dimension of the simplex is, then its dimension is k minus 1. Okay, so if it is a two points P1, P2, it is a one dimensional simplex, a segment. Okay, 1 point 0 dimensional simplex, it will be vertices. Okay. Just to make it like k minus 1, this confusion to remove, normally when I write from now on simplices, I will write it like p naught to pk, and I will say the dimension of the simplex will be k. Okay. Start with 0, that is it. Good. So, what are the faces of the simplex? Faces. So, we will come to this term faces again and again. So, let me call faces of a simplex. So, again let us say you have a simplex p naught to pk. Let I be an index set, which is a subset of 0 to k. Okay. So, now look at the convex hull of this object, of this set. So, convex hull of A is what we are interested in. So, convex hull of the points whose indices are in the set capital I. Okay. All of these will be faces of, this will generate, if you look at it, this will be subsets of the sigma, right. So, is it clear why it will be subset of sigma? Yes, no, it is not clear. So, or at least the subset condition is also not clear, is it? So, this is something we discussed, right. A, if it is A is a subset of B, then the convex hull of A will be a subset of convex hull of B, right. So, convex hull of A contains what? It contains points of the form some lambda I p I, where I belongs to the index set I, right, such that lambda I is greater than or equal to 0 and summation lambda I belonging to capital I is equal to 1. So, these are linear combinations of p i's only, right. You can like, I can make these indices go from 0 to k only. What will I do? The ones that are not in I, capital I will make them 0, those lambda i's. Okay. So, try to convince yourself that this is, they will be, at least this convex hull of A will be a subset of sigma. Okay. So, let us take an example and see. Okay. So, what are we talking about? So, again let us take the example of a tetrahedron in R3. So, you have P naught, P1, P2, P3. Okay. So, what are the faces of this tetrahedron? Okay. A tetrahedron itself will be a face of itself, right. Sigma will be a face of sigma. Okay. This edge P naught P2, is this a face? Yes, no, of sigma, just the edge connecting P naught P2. Why not? If I take the index set I to be 0 2, the convex hull of these 2 points will be this edge, right. What about this face? P naught, P2, P3, is this a face? Yes, no. Why? The index set will be what in that case? 0, 2, 3. Okay. Good. So, how many faces will it have, this convex hull, this simplex sigma? So, okay, one thing I should have mentioned when I said, when I mentioned this index set I assume it to be non-empty. Okay. A convex hull of an empty set does not make sense to even define. Okay, so I has to be non-empty. Okay, it is a subset of 0 to k, and I is non-empty. Okay, so how many faces will this simplex have? So, this is a question. Okay, when you go back, check how to answer this. How many faces will this simplex have? How many faces does a k simplex have? Pardon? Can you come again? Oh, so when I say k simplex means a simplex whose dimension is k. Okay, also, so let now take a triangle case first. So it will be easier to draw. So here we have, so all of this is here. So P naught, P1, P2. So I take another subset inside this red thing. Okay, is this a face of this simplex sigma, this triangle? No? Yes? No. Okay. It is not, right? It is not a convex hull of subset of vertices of the simplex. It's okay? Okay. Few simple properties to check, simple properties to verify. So before I do that, let me define. Okay. So I have defined that the dimension of a simplex will be what? Dimension of the simplex will be k, right? That is basically number of vertices that are involved in making the simplex minus 1. So we are starting with P naught to Pk, right? So what is the dimension of this simplex? This P naught P2. By the way, P naught P2 is a face of the simplex. Is it itself a simplex also or not? Yes, right. It is a convex hull of these 2 points, right? What about this? Is this a simplex? This red thing? It is a simplex. Obviously, it is a. If it is, I wanted to draw a triangle. Okay, so but okay, whatever. It is a convex hull of these 3 black points, but it can be a simplex, but does not have to be a face of sigma. These 3 black dots are affinely independent, right? Okay. So simple things to verify. Okay, so let us say I take so one, let us say I be the again non-empty subset of this 0 to k. So the dimension. So first thing verify is face convex hull of, let me write as AI. AI means all those AI is equal to all those PI's such that I belong to capital I. Okay. This itself will be convex. This is also a simplex of dimension. What will be the dimension? Size of I minus 1. Okay. What else did I wanted to verify? Okay, let me try to think. No, let me just not properties, but this simple property is good enough for the time being. Okay. If you have a question, ask me. Okay. I want to go slow. Okay. I don't want to hurry because these things will be used in like second half of today's talk and also tomorrow's talk. So now we can define what is called geometric simplicial complex. By the way, these objects that I have defined, actually I was talking about simplex. These are what are called geometric simplex. So you will be clear why it's called geometric. But when I define what is an abstract simplicial complex or abstract simplex, but currently just think of it like just take the name for granted, it's geometric simplex. So you can define what is called geometric simplicial complex I want to define. What is it? It will be a collection of simplices in RD such that the following holds, following two property holds. Okay. First one, faces of a simplex in so let me denote this simplicial complex by, let us say, K. Faces of simplices in of a simplex in K is also contained in K. So, I will give you an example and I will show you how to contained in K. The second thing is either intersection of two faces of two simplexes in K is either empty or it is also a face in K or is also simplex in K. So, when I talk about simplicial complex, I will sometimes use the word face and simplex in the complex, they are anonymous, okay? In the sense, they are the same thing. They mean sometimes I will call it simplices in the complex, simplicial complex, or I will say faces in the simplicial complex, okay? Just like this. Okay. I will use them interchangeably, okay? So, let's see some examples of a simplicial complex, okay, and what are not a simplicial complex. So, let's say I have a simplicial complex like this. P0, P1, P2, P3, P4. So, let me write down the simplicial complexes. So, one is sigma 1 is P0, P1. So, let me write first. So, let me write them lightly. So, P0 is 1, P1, P2, P3, P4. Oops, sorry. Then you have P0, P1, P1, P2, P0, P2. Also you have P3, P4. Okay. So, these are the simplices here. So, is this a complex? Is it a simplicial complex? So, we have a collection of simplices. We have that or do not have it? These are simplices, right? P0 is a 0 dimensional simplex, P1 is a 0 dimensional simplex, P0, P1 is a 1 dimensional simplex, right? Is it a simplicial complex? See, one property here holds, that all the subsets are given any no, the inside thing is not there, just the skeleton, the triangle is not there, okay? The boundary, like the three edges are there of the triangle, inside is not there. If suppose I included inside, so since if you are interested in including things inside, I am perfectly fine with that also, but P0, P1, P2, no confusion. So, with this, is it a simplicial complex? Subset property holds, right? But is the intersection property holding? Intersection of this simplex and this is basically this edge. This is not in the complex, right? This part is not included as a simplex in your set. This is a perfectly fine collection of simplices, but it is not a simplicial complex. What would have been a simplicial complex? It should look something like this. Maybe this triangle is also present. Okay. So, all the edges are included, all the vertices, let me draw the vertices in black, all the vertices are included, I have included all the vertices, this corresponding red edges I have included in the collection, and this one triangle I have included in the collection. This will be a simplicial complex. A face of a face is in the complex, right? this edge has two faces, like itself as a face, and these two black points, both are in the complex. This triangle has these red edges, they are in the complex. Inside thing is anywhere in the complex, and the 3 red dots are also in the complex. So this is a simplicial complex. Okay, so let me see one more example. What about this? This you have one triangle. So you have this. I have included this black. Can you see the black dots I am making on the back? It's clear, right? And the other one is, so by when I do this black dots, this means these are in the complex. So how do I do? Okay. So let me tell you what is not. Okay, so this triangle is present, this triangle is present, and the corresponding edges are present. But let's call this P0, P1. P0, P1 is not in the complex. Okay. Is this a simplicial complex then? Suppose I included P0, P1. Will it become a simplicial complex? I am drawing everything in R2. I mean, this diagram is in R2. Is it a simplicial complex? Yes? No? What is it? See, this object, this convex hull is present, right? Okay? It is made up of 4 points. They cannot be affinely independent. It is more than d plus 1, d is equal to 2. It should be at most 3. So even if I included this edge, you are not making it into a simplicial complex. It's okay. So like we defined the dimension of simplices, you can define dimension of simplicial, geometric simplicial complex. Okay. So this will be basically dimension. This is equal to maximum dimension of a simplex contained in the complex. The simplicial complex. Okay. So let's say do one more diagram and see. Okay. So you have these vertices, this triangle, one edge, one isolated vertex. So I have included all of the faces in such a way that this is a simplicial complex. What is the dimension of this simplicial complex? By the way, simplicial complex doesn't have to be connected or anything. Okay. So what is the dimension of the simplicial complex? What is the maximum dimension of a simplex in this complex? 2, right? You have a triangle. Everything else is dimension less than 2. So dimension of this complex is 2. Okay. So again, for a simplicial complex, you can define what is called jth skeleton. Jth skeleton of a complex, simplicial complex. This is what you do with this. So this is a sub complex. So it's a subset of the collection of simplices that are included in K. So I want to understand jth skeleton of K, let's say. Okay. What will I do? I will take all the simplices of dimension less than equal to K that are contained in K and included it K prime, and we call that K prime to be J skeleton. So let's say what will be the one skeleton of this complex? It will be basically the vertices and the edges. This is the one skeleton. The triangle won't be included. So in terms of subsets, K prime is supposed to be a subset of K. Remember, I have to include all of them properly. So, question 2, is the jth skeleton also a simplicial complex of K, also a simplicial complex? So, I have a simplicial complex. I have computed its jth skeleton. Will that also be a simplicial complex? Pardon? Can you come again? Jth skeleton will be, so see, simplicial complexes will be collection of simplices, right? So, what will be the jth skeleton? It will be a subcollection of the subcollection of K, okay? Subset of the, I will extract a subset out from K. What are the simplices I will take? I will take all the simplices from K whose dimension is less than equal to K. That will be defined as a jth skeleton. So, this one, see this one had 0 dimensional simplices, 1 dimensional simplices and a 2 dimensional simplices. One skeleton of it will have all the 1 dimensional, 0 dimensional simplices and all the 1 dimensional. Triangle is not present, interior is not present. So, these are what are called geometric simplicial complexes. Okay. So, there is another thing what is called abstract simplicial complexes. These are much easier to define. Also, when you do computations, you are basically working with like geometric computation, okay, with simplicial complexes. You are basically working with most of the time with abstract simplicial complexes. Okay. Obviously, they will have a geometric representation and stuff, but normally the game you play is a game of subsets. So, you will see why I am saying subsets, abstract simplicial complexes. So, let us say I have this set, I will denote by this box n to be numbers from 1 to n. Okay. Okay. So, what will be an abstract simplicial complex? Abstract simplicial complex will be collection of subsets of n which are downward closed. That is it. What do I mean by that? If a subset is present, so I will call, let us again K, let me write like tilde to denote abstract simplicial complex. So, K tilde will be a subset of first n numbers, okay. It will be a abstract simplicial complex if if some sigma which is a subset of 1 to n is present in K tilde, all of its subsets are present in K tilde. Does it make sense what I am saying? Okay. Yeah. I just give one example to see. Okay. So, let us say I am working with 4. Then let us say my K tilde is, you include the empty set, downward closed, all subsets is what I am including, and then let us say include, and sometimes they include the empty set, sometimes do not, but I want to work with this simplified definition. So, I am explaining. So, let us say I include 1, 2, 1, 2, 3, 1. So, when I am purposefully writing this notation as box, I should not use box then, this will be more confusion. Just let me do this, let me use bracket. Subsets is what we are working with. Okay, so good. Is this a simplicial complex? Abstract simplicial complex? These are K tilde is a subset of first 4 numbers 1, 2, 3, 4. Okay. What did I say? What is the definition of downward close? Downward close means if a subset is present, then all of its subsets are also present in the complex. If 3, 1 is present, all of its subsets should be present. Is 3 present? So, is it a simplicial complex, abstract simplicial complex? No. You can make it by including 3. Is it clear now? All the subsets should be present. Pardon? Yeah, so by definition it is a abstract simplicial complex. With this definition it is a simplicial complex. There are slight variations where you can do is you take out the empty set, but you have to make these changes in the definition, but does not help. It is better to keep this definition as simple as possible, because we are not losing out on anything with this definition. Okay. So, you can say, I mean, you can change the definition, K be a collection of subsets of this. For every non-empty subset that is present, all of its non-empty subsets should also be present. I add too many words, I do not want to write. Okay. Just to make it work, just include the empty set in the set and we will be done. There is nothing vacuously true. By this definition, it is true. Empty set is a subset of empty set, no? Not vacuously, it is true. Okay. Okay. So, it is both subset and as well as disjoint with empty set. So, it is an interesting object. Okay. So, now in the simplicial complex, okay, you have collection of subsets, right? It will be a collection of subsets satisfying some property. Collection of subsets satisfying some property. I do not want to write that property. Okay. Satisfying some property. So, let us say sigma is contained in K tilde. Sigma is some subset of first 1 to n numbers. Huh? So, I want to call this is a subset, but I will be, since I am working with the framework of simplicial complex and we are building from the geometric case, I will call this sometimes faces, sometimes simplices. These are called abstract simplices. Okay. Rather than calling them subsets, I will call them either faces of K tilde or simplices of simplex of K tilde. Okay. Then you can, as with the geometric case, it is natural to ask what will be the dimension of sigma. We defined a dimension of a geometric simplex, right? I want to define the dimension of abstract simplex also. So, what do you think should be the dimension? What should be the natural extension of the definition that we have already seen for geometric case? See, these vertices are basically the points contained in sigma are basically playing the role of vertices. See, in the geometric case also, once I tell you the vertices of the simplex, I do not have to tell you anything else. You know the simplex is completely defined. Vertices of a simplex completely characterize the simplex. If I know the vertices, I know all the geometric properties of the simplex, right? What will be its faces, what is the geometric object it represents, it will be the convex hull of the vertices, right? So, like knowing the vertices is good enough. And how did we define the dimension? We said the number of vertices minus 1. Here you will say size of sigma minus 1 will be the dimension. This denotes the size of the number of size of the set minus 1. It's okay. So, again then you can ask what will be the dimension of K tilde. Yeah, so I mean the thing is, it's a natural thing you can say, see when you define a geometric simplex, you are not only saying the vertices, but you are saying, oh, it is a convex hull of the vertices. But what I am saying is, since we start with since we are just looking at convex hull of the points, once I know the points, I am done. Only thing I have to know, the point should be affinely independent. So, I give you some set of points, I say these are the vertices of your simplex, and you check, okay, these are affinely independent, okay, I now know it is a, what is the valid simplex, okay, with these as the vertices. I do not have to exactly know what are the faces or anything, I can compute the faces once I know the vertices or the geometric object it represent, right. So, vertices completely determine your geometric simplex. Here also the elements contained in sigma will determine your simplex. There, how did we define the dimension? For the geometric simplex, we said number of vertices minus 1. See, I could have defined that dimension in slightly different way also. I could have said, let us say I take a valid simplex, geometric simplex. The dimension of the geometric simplex will be the minimum dimension of the affine space that contains this simplex. Will it be different? These are two different definitions I am telling you now, right. One is number of vertices minus 1, one I am saying is minimum dimension of the affine space that contains this simplex. Are they equal or not equal? They are equal, right. Normally when you do for the geometric case, people like to do it dimension of the minimum affine space that contains this, but I purposefully wanted to say, since I have already started with the case that the vertices are affinely independent, that is why I said, okay, take it to be number of vertices minus 1. So that when I do it here, it does not sound surprising. Here what you do? Here there are no geometric things, here just here you have subsets of 1 to n you have, right. So how do I define the dimension of a simplex? I say number of elements in sigma minus 1. That is how you define. And how should you define the dimension of our abstract simplicial complex K tilde? Dimension of the maximum, yeah, so dot dot dot, I am not writing it, it will be the dimension of the maximum dimension of a simplex contained in K tilde. There is a connection which is something I will be proving now. Yeah. There is something called geometric representation of abstract simplicial complex. Okay. All abstract geometric simplicial complexes, we are working with finite, okay, only, so do not have to worry about infinite case. All the simplicial complex that we will be working with will have a geometric representation in some RD. I will tell you what that D will be. I am not saying that is a minimal representation or anything, I am saying there is a representation, and if there is a representation you can also find a minimal representation. I do not care about the minimal one in this stuff. Okay. So, before I do that, let me check. Yeah, so this is like a folklore theorem. So, let me, well known, I do not know what is the reference. Did I know? No, I do not know the exact reference for this. So, what it says is, let us say if the dimension of K tilde is T, then it has a representation as a geometric complex geometric simplicial complex in K to the R to the power 2t plus 1. It's okay. So now see, this statement is not complete. The natural question is asked, what the hell are you writing about geometric representation? Okay. You have not explained what is the geometric representation of an abstract simplicial complex. So intuitively, what you think should be the, what should be the definition of a geometric representation of an abstract simplicial complex? What should it be? It should be a geometric simplicial complex for each face in K tilde. So, and let us say it is represented in some RD, and let us call that geometric simplicial complex to be K. So, for each simplex, like dimension j simplex in k tilde, you have a geometric k simplex in k, and it should be one to one map. It should also preserve the intersection property. Okay. So let us do some examples before we see the proof of this. So let us do an example. Okay. So let us say I do the I consider the complex with this, let us say. Just this. Okay. What will be its geometric representation? One geometric representation will be 3 vertices and 1, 2. So, let us call this 1, 2, 3 and 1, 3. Okay. So, I want a representation like this. Okay. So, if there are two simplices, sigma. So let's say write like this. So k tilde is your abstract simplicial complex, k is your geometric simplicial complex, and I say they are, k is a geometric representation of k tilde. Okay. What are the things you want it to satisfy? And let us say the map will be defined by, let us say, pi. Okay. So sigma belong to k tilde will be mapped to pi sigma belong to k, but this will be a geometric simplex in k, contained in k. See, k will be collection of geometric simplices, k tilde will be collection of abstract simplices. You want the map to be one to one also. Not only that, what you want is simplicial properties should be satisfied all through. Okay. So what you want is, let us take sigma prime. So let us take pi of sigma intersection sigma prime. So this is a simplex in k tilde, because this is a subset of sigma and sigma prime, and I am saying sigma prime and sigma both are contained in k tilde. So this is also this object is contained in k tilde. This should also be a simplex in k. So what you basically want is each abstract simplex to be mapped to a geometric simplex, and their intersection of any two or the subsets of any two should be aligned with lower simplices in the geometric case also. Right? That is the main idea. Is it clear what we are trying to do? Okay. So now how to prove that result? Proof. If you have a question, just ask. Everyone gets it? So let us do one more example. Okay. So let us do this. One, two, three, 4, 5, and let us say the geometric abstract one be this 1 to 5, and then this 1 2, 1 3, 1 2, 1 3, 5 4. Is this a geometric representation of this simplicial complex, abstract simplicial complex? Firstly, this itself is not a simplicial complex. This is intersecting. Okay. So it won't be. This could have been a proper representation. So if I just, if 5 was here. Okay. So let us see a proof of this. So one here I want to use one simple idea. Okay. So let us say you are asked to find n points. Forget about this geometric representation question, does not matter. Okay. You are asked to find n points give me n points, n, think of it as bigger than, much bigger than D, okay, n points in RD such that any D plus 1 point, any subset of D plus 1, of subset of size less than or equal to D plus 1 points will be affinely independent. Can you do it? Can this be done? So, let us take the simplest case. I want to generate n points in R2 such that no 3 points are collinear. Can we do it? No, it is not possible to do. Yes. I should have some answer. Yes, no, maybe, not sure. Not sure is also a perfectly fine answer, by the way. Okay? Not clear how to do it? You can do it, right? Yeah. So let us take that as a black box. Okay? In any dimension, I can always generate, for any given n, I can always generate n points such that any subset of less than or equal to D plus 1 points will be affinely independent. Okay? That is the only thing I will use for this proof and nothing else. Okay. So, let us take, so we have this geometric complex whose vertex set is this first n numbers, and the dimension of this complex is T, right. So, I will make, so let us make our life even slightly more difficult. Let us assume K tilde contains all subsets of size T plus 1. Does it make sense what I am saying? Let K tilde contain all subsets of size T plus 1. It will be a simplicial complex, subset property, downward close, holding, no problem. Am I making the problem harder or simpler when I am doing this? Harder, I am adding more objects, right, that you have to embed properly. Okay? So, I am making myself, my life only harder, but I want to know whether you can do it or not. If I can do this, then I will be able to embed all simplicial complex whose dimension is at most T on n vertices, right. So, let us try this, the more harder thing first. Okay. What I do is, I generate n points in RD such that there any subset of D plus 1 points are affinely independent. So, have you introduced the general position property? So, let us, so this is what is called general position. Okay. For in general dimension D, this is called general position. See, in CG, there are 100 different definitions of general position. You make definition of a general position that helps your case for the problem that you are trying to solve. Here it is only the linear case. So, general position in R2 was what? No 3 points on a line, right. So, what I am basically saying, any 3 points should be, any subset of 3 or less points should be affinely independent, right, in R2. Here we are saying any subset of size less than or equal to D plus 1 should be affinely independent. Okay. Let us do this, and let us do a map from, like, I map the vertex set 1 to P1, 2 to P2, like this, n to Pn. So, I define the map pi I. So, I will define the map on the vertices, that is it. Pi I goes to Pi. Okay? And now I say I already have a geometry representation. Why is that the case? Pardon? Can you come again? So, you can see it directly, so it is good. So, he sees it, but so one first thing is, if I take a simplex in abstract simplex in k tilde, I should get a simplex in k. Okay. So, first I have to define k. Okay, I have defined the vertices of k, it's good. What will be the simplexes in k? All t dimensional simplexes that I can make with vertices p1 to pn. Okay, so what is k? All t dimensional simplexes that I can make with p1 to pn, right. So, will all t so if I take, let's say, first p1 to pt point, p1 to pt plus 1, sorry, this will be a k simplex, right, t simplex, right, in k. Is it a valid simplex first? Oh, so let me do one. So, d here is, sorry, 2t plus 1, okay, sorry, okay. So, let us say I take p1 to pt plus 1, okay. This simplex is, so at least the convex hull of this is included in k, right. But for it to be a valid simplex, first it has to be a valid simplex itself. What is the first thing I need for it to be a valid simplex? The only thing I need it to be a valid simplex? Affinely independent. Is p1 to pt t plus 1 affinely independent? Yes, because I have said any subset of size d plus 1 is affinely independent, size less than or equal to d plus 1, which is equal to 2t plus 2, which is bigger than t plus 1. So, good. So, I have a proper simplices. But just adding proper simplices, is it good enough? See, I can add proper simplices, but they are intersecting in the interior. Then how will I manage? I have two proper simplices, I have two proper triangles. They are individually they are proper simplices, but they have an intersection, right? So, like even in an edge case, right? This edge is a proper simplex, this edge is a proper simplex. But let us say in R2, I have included both of them. There is an intersection, right? Obviously, it is not a proper simplicial complex. So, what do I have to show for it to be a proper simplicial complex? I take two t dimensional simplices and show they don't intersect in the interior. If at all they intersect, they should intersect in the on a face. Right? Then I will be done. Nothing like this. They are allowed to intersect, not intersect, or if at all intersect, it can be intersected. So, this is one, these are valid thing. Okay. So, this is the only thing I have to show. If I can show that the geometric simplices that I am generating in K, that K is a valid simplicial complex, geometric simplicial complex, then this map is well defined and you get a geometric representation of K tilde, right. Okay. So, how do I show that? So, let us take sigma 1 which is equal to P1 to, so let me write P naught, I like to do it with P naught. So, P naught to Pt and sigma 2 P naught prime to Pt prime. Now, do not please say that is P naught prime in the set P1 to Pn. Yes, P naught prime is also in the set P1 to Pn. Okay, I just wanted to write it in this way. Or let me maybe rather than doing this confusing thing, let me write it like this. Let us take it to be t plus 1 to how far it will go to t plus 1. Okay, and I want to show that these two simplices. I have taken two arbitrary simplices. I want to show they intersect properly. In the sense, either they intersect on a face or they intersect. Let us take the, I will work out one case. If you can, other one follows in the same way. Okay, that is an exercise for you to complete. Let us do the simplest case. Assume that the set P naught to Pt and Pt plus 1 to P of 2t plus 1 is disjoint. Disjoint sets. Okay. This is the case I will be working with. Okay. The other one actually follows the same way. Okay. So, now how will I show? It will be a proper, the intersection will be a proper intersection. So, now let us build another simplex. Okay. Simplex in RD. This simplex is not in K, okay, whose vertices are P naught to Pt and till P of 2t plus 1. Is this a valid simplex? This simplex is not in K, by the way. This simplex is a simplex in just in RD. It is a geometric simplex in RD, where D is equal to 2t plus 1. Is this a valid simplex or not? What is the only thing I need for it to be a valid simplex? Pardon? Affine independence. So, when you know the correct answer, why are you like shaky here? So, are these points affinely independent? Not. That is how we constructed the point set, right? Right, the way we have constructed the point set, okay, they are affinely independent. So, then sigma prime is a valid geometric simplex. Okay. So, now this is the thing I want to argue now. Now, I say, see, then sigma and sigma 1 are faces of sigma prime. Right. My claim is now, before I prove this, my claim is, let us say I have a simplex sigma, okay, and I am making a simplicial complex out of sigma. How? I have the simplex sigma and the complex, let me write the complex at K sigma to be all faces of sigma. Okay. You have a geometric simplex sigma and K sigma is all the faces of sigma. Is this a valid simplicial complex? It is a valid simplicial complex. That means two faces cannot intersect in the interior. They are either they are disjoint or they intersect at the surface of the two faces. That means, see, sigma 1 and sigma 2 are faces of sigma prime. Sigma 1, sigma 2 are faces of sigma prime. What is sigma 1, sigma 2? Just go, let us see the sigma 1 and sigma 2 are faces of sigma prime. So, that means either they are intersecting on a subface or disjoint. So, they sigma 1 and sigma 2 are not intersecting in the interior. So, we get a valid geometric representation. By the way, when I said I include in K, I include all the simplices of size of dimension T, what should I have said? I made a mistake there. I should have said in K, I have all the simplices of dimension less than equal to T. Okay? If I just have, let us say, if I just have this simplex in itself is not a simplicial complex. A simplicial complex should also contain all the subfaces. So, to make it a simplicial, this is a simplicial complex. You have some question? This sigma has nothing to do with the sigma 1, sigma 2. What I am saying, take any geometric simplex. Okay? Is that a simplicial complex? It is not. If that is contained as a singleton set, it is not. Okay? You have to include all its faces. Then it becomes a set that includes sigma and all its faces will be a simplicial complex. That is basically this K sigma that I have defined here. Right? So, when I said in K that in K includes all the simplices of dimension T, I was wrong, because I should have said include in K all the simplices of dimension less than equal to T. but will the proof change when I do that? So try to go and think, it won't change. This actually completes the proof. Okay. So now you get a geometric representation. Good. So just one second, where is the paper? Okay, sorry. What did I want to cover? This is a folklore result and it's used everywhere, but yeah. So similarly, you can define, like let's say for abstract, I am not defining it now, for both for geometric and abstract simplicial complex, you define what is called isomorphism. Okay, so what is, like, let's say you have k prime, k prime are either both geometric or abstract simplicial complex. I call them, I said that I will say that they are isomorphic if there is a map, one-to-one map from k to k prime. Okay, taking simplices here to simplices here, the same dimension simplices. So simplices here will be taken to a same dimension simplices here, and there it will be one-to-one. They intersect nicely on the map. Okay, whatever we have defined. I don't want to define it formally. It's not much. I won't be using it that much. Which dimension should be pt plus 1? Can you come again? Where did we use the fact that the point set is, I said, like any set of size d plus 1, any subset of size d plus 1 from p1 to pn is affinely independent. That is the thing. See, when I said that this simplex sigma prime whose dimension is d plus 1, see d is equal to 2t plus 1, right? I said this is a valid simplex, geometric simplex. It won't be a valid geometric simplex unless these points are affinely independent. That is where we use it. Yeah, so the basic idea is what you want, the main idea of this proof is, what you want is, you want to make sure that all, if I take any two simplex of dimension t, I want to make sure they are faces of a valid simplex in Rd, R to the R 2t plus 1. If I take two t simplex that gets mapped from this abstract to this two abstract simplex get mapped to these two geometric simplex, I want them to be valid faces of a simplex. Then I don't have to worry about this bad intersection property. Right? Once I can show that, I want to use this. But let's say I take two simplex, each of dimension t, and I want it to be a face of a simplex. Their vertex set of sigma and sigma prime, sigma 1 and sigma 2 can be disjoint. This has t plus 1 vertices, this has t plus 1 vertices. So the geometric complex, that geometric simplex that I will be looking at should have at least 2t plus 2 vertices. Right? You have sigma 1 and sigma 2. See, their vertices can, like, they may have common faces. Then if I take the union of vertices, it will be a size less than 2t plus 2. But at worst case, they may be disjoint, the vertex set. Then the size of the vertex set is 2t plus 2. These vertices has to be vertices of the geometric simplex also. So the geometric simplex should include at least 2t plus 2 points. The vertices, size of the vertex should be at least 2t plus 2 points. So this is 2t plus 1. This is where I can have a valid simplex